Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of tornadoes and trying to predict the magnitude of a given tornado based on a series of features. So I'm just going to hop right into the notebook. We're going to use NumPy and pandas for working with the data, and then for pre-processing we'll just use the train test split function and standard scalar from sklearn. Then the three models we'll use today is a simple linear regression model, a linear regression model with L2 regularization, also known as ridge regression, and a linear regression model with L1 regularization, also known as lasso regression. So I'll go ahead and import all of that, and we can load in the data using pandas.readcsv. And we can grab the file path to the CSV file right up here. I'll paste that in, and we can take a look. Let me just zoom this up. Alright, so here's the data. We have 22 columns in total. Some of these are categorical, some of these are numerical. We're going to get to pre-processing it in just a moment. I would like to note that in the description of the dataset here, we have some metadata available to us, which will come in handy when trying to understand what the columns mean. So let's get a little more information on the dataset with data.info. So here we can see there are actually no missing values in the dataset, at least not values that have been encoded as NaN. And we also have 3 object columns in total. Now these are not the only categoricals we have. There actually are other categoricals besides the object columns, and we can see that here. For example, TZ is time zone. Even though it has been encoded as numbers, it is still categorical, so we have to make sure that we catch those when we're encoding. Alright, so I'm going to start pre-processing here. I'm going to create a function called pre-process inputs that's going to take in a data frame. It's going to make a copy of the data frame, and then at the end it will return the data frame. So right now all that's going to do is make a copy, and I'm going to pass in data and store the processed version in X. So right now X is just a copy of data, but now as we go through the pre-processing steps, we can see the result down here. Alright, so let's look at what the first thing to do might be. Well, the one thing that stands out immediately is that we have this date column. However, we already have the year, month, and day extracted from it and put in their own columns. So this is sort of a redundant feature, right? We don't need this. So I'm going to go and drop the date column. Drop date column, and we can do this with df .drop date from axis1. Now we can see X no longer has date on there, and we can continue. So here is, this is an interesting one. If we look at the description for OM, it's a tornado number. It says a count of tornadoes during the year. Prior to 2007, these numbers were assigned to the tornado as the information arrived to the NWS database. Since 2007, the numbers may have been assigned in sequential order after event date/times are converted to CST. However, do not use OM to count the sequence of tornadoes through the year, as sometimes new entries have come in late or corrections are made and the data are not resequenced. So it's a bit of an interesting column, because these are unique identifiers for the tornado, but they also represent something about how many tornadoes there are in a certain year, because the count resets each year. Now I tried doing some interesting feature engineering with these, and it does not seem to improve the model. It actually makes it perform worse. So it seems like this can just sort of be interpreted as an ID column, and is not really going to contribute much to the our ability to predict the magnitude of the tornado. So I'm going to drop that over here. Drop ID column. And there's actually one more in here, the STN. If we look at STN, it is, no, not STN. Oh yeah, it is. Okay, state number, number of this tornado in this state in this year. So it's very similar. It's a sequential ordering of tornadoes, but they're basically each given their own identifier. And this also, in addition, it was discontinued in 2008. So you see we have all zeros down here in the later years. This column is also, it seems to be inhibiting the performance of the model. So I'm going to go and drop that too. And I'll call that an ID column also, so I'll say drop ID columns and drop. The first one is OM, and the next one is STN. And we're dropping from axis 1, which is the column axis. Alright, and now we're left with this. And I believe everything here is fairly relevant to what we're trying to do. The one thing I'm a bit unsure of is the FC column. If we look at that, basically it's talking about it's going to be 0 if the F skill rating is unaltered, and 1 if the rating was unknown. So it's sort of like a missing value flag for the F skill column. However, the F skill column, where is it? F skill. Here, the F skill column, which is supposed to come after state number and before injuries, doesn't exist. It's not included in the dataset. So this is a missing value flag for a column that we don't have. Now, I don't see how that's really relevant, so we're just going to go ahead and drop it, since, yeah, it doesn't seem very useful, since we don't actually have the column it's talking about. Drop FC column, say irrelevant. df equals df.drop FC axis 1. And I'll say this one is because it's redundant. Alright, so I think we've dropped all the columns we need to worry about. So for the rest, we want to think about encoding. We know we have no missing values. A lot of these are numeric, which means they're already encoded. They're just a continuous range variable. This is the length and width of the tornado, so that's a continuous range value. These are the starting and the starting latitude and longitude, so that's continuous range. This is the ending latitude and longitude, so that's continuous range. This is the loss in a monetary loss incurred by the tornado, and this is the monetary crop loss incurred by the tornado. So those are also both ordinal features, so they don't need to be encoded. This is injuries, fatalities. They're all also count variables, so they don't need to be encoded. Magnitude, we're not encoding simply because that's going to be what we're trying to predict. And then here, STF. So let's look what STF is. This is the FIPS number, sort of like a zip code. These are unique identifiers for locations within the state. And so these are actually categorical. So we're going to want to encode these, probably with a one-hot encoding. Then the state, this is clearly categorical as well. So these are both nominal features, meaning their values do not have any ordering to them. Then time zone, we saw that before, that's also going to be nominal. So it looks like these three here are our nominal features that we'd like to encode. Everything else is numerical. We have the year, month, day, that's also numerical, and then the time, which we're going to I'd probably extract the hour and minute out of it and use those as features. So what I think I'll do is we'll do the time first, we'll take out those numeric features, and then we'll do the one-hot encoding to these three columns. So let's extract time features. So to do this, I'm going to grab one of these times, and I'm going to show you that we can use pandas.toDateTime to pass in a string that looks like that, and we'll get back a datetime object. So it's using the current date, but we don't have to worry about that because we're not going to use the date part of it. We can call .hour on it to get the hour, and .minute to get the minute. And if we wanted, we can do .second as well, although I'm not going to get second. I'm not even sure if seconds are encoded here. Second really doesn't have much value to us. So I'll take out the hour and minute, see if we can get something out of that. And I want to note that we can pass in a whole column here if we want. So let's say the time column. And now the whole column gets converted to datetime. So now we can apply a function to each element. Let's call each element x, and we can just take x dot hour. And that will just give us the hour for each example. So you can see this 11 o'clock went to 11, this 11:55 went to 11, this 16 o'clock went to 16, and so on. So let's do that up here. I'm going to take the time column, and I'm going to use pandas.toDateTime on it. And then I'm going to take I'm going to do what I'm doing down here by applying a lambda function to it and mapping x to x.hour. And I'm going to store that result, which looks like this, in its own column called hour. Then we'll do the same thing for minute, and then we'll be done. So this will be the minute column, and we just get x.minute. And once we've done that, we can drop the time column, since we took all the information we want out of it. Alright, now let's take a look. You can see time column is gone, and we now have hour and minute on the end. So everything is in numeric form except for this time zone, state, and state FIPS code columns. So for these, we're going to use one-hot encoding. And one-hot encoding, we'll use the getDummies function. Let's take the state, for example. You can see that each state now gets its own column, and a 1 in a given location will signify the original value of that example. So here there's a 1 for example 3, and that corresponds to the Arizona value, and that just means over here in example 3 we originally had an Arizona value for state. So we're going to use this to encode these categoricals, and I want to create a function that's going to do this for us since we have 3 columns we want to do it for. It's going to take in a data frame and a column that we'd like to encode. We'll start off by creating a copy of the data frame so we're not modifying the original version. And then we'll create some dummies using pandas.getDummies like we just did. Now I'd like to point out that we can include a prefix here. Let's make it the same as the column name. And that will just put st at the beginning of each column so that we know where these columns are coming from. We just want to make it extra clear that these are coming from the original st column. So up here in our function, I'm going to call getDummies on df subcolumn and include a prefix, which will be the same as the column name. And then we will concatenate together the new dummy columns we just created onto our original dataset. So for that, we can use pandas.concat, and we're going to concatenate df and dummies along axis 1, which means side by side. And then we're going to drop the original column from which we created the dummies. And after that, we can return df. So here's our function for one-hot encoding, and down here we're going to perform it on one-hot encode the categorical, or I'll say nominal features. Alright, and so those nominal features were time zone, state, and state FIPS number. So here they are. So what I'm going to do is for column in, and I'll make them into a list. We'll call one-hot encode, store the result in df, and we pass in df and the column equals column, so whichever one we're iterating through. Alright, and now if we run this, we have 124 columns. You see on the end here, we have all of our one-hot encoded columns here. It's quite a few of them, but that's okay. And then all of our original data is still right here. So the whole data set is in numeric form now. So it's almost ready to feed into our model. The last thing we're going to do is scale the data. So before I do that, I'm going to split it. We're going to split df into x and y. Y is what we're trying to predict, and we're doing this now because we don't want to scale y. Y is our target, and we want to leave that untouched so that we can predict it correctly. And so that's going to be the magnitude, which is the mag column. Technically, we could treat this as a classification task, as these are discrete values. You could consider it as classifying between magnitudes, but we're going to treat it like a regression task. So let's take the magnitude column and store that in y, and then x will be all the rest of the data. So I'm going to drop magnitude and store that in x. Then we'll do our train test split. So this will take some percentage of the data and put it in the train set, and the rest of the data will be put in the test set. So I'm creating 4 new sets of the data here: xtrain, xtest, ytrain, and ytest. And we're going to use the train test split function from sklearn that will give us, will specify what we want to split, which is x and y, specify a train size of 70%. Then we'll keep shuffle on, and we'll include a random state so that the shuffle and therefore the split is always done in the same way. and then we're ready to scale. So I'm just scaling x, right? We're not scaling y, and I'm going to create a standard scalar object. This is from sklearn, and a standard scalar will just give each column a mean of 0 and a variance of 1. And models, a lot of models prefer when you scale. So we'll fit the scalar just to the train set, and we'll transform both xtrain and xtest using the fit we have to the train set. So we sort of want to pretend we don't have access to the train set at the time, to the test set at the time of pre-processing. So we're calling scalar.transform on each of these. This one is going to be xtest. And the scalar.transform function actually returns a numpy array. So if we return this now, you'll see x, oh sorry, I'm returning df still. Let me return these 4 values. So I'll get them back over here, and then we can take a look at xtrain, and you'll see it's a numpy array. So that's fine, we could feed it into our model if we want, but I still want to get a nice look at it, so let's keep it as a data frame with pandas.dataframe, and we'll keep the index and columns names the same as they were before. So index equals xtrain.index, columns equals xtrain.columns, and down below I'm just going to change these to xtest. Alright, now we return this, we should just have a data frame again with the right column names and indices. And now if we look at the describe function of this data frame, we can see the means are all very close to 0. They're all very, very close to 0. And the standard deviations, which are just the square root of the variance, is very close to 1. So let's also look at ytrain. These are our labels. We can look at how many unique values we have in there, and you can see we're trying to perform a regression across a range from 0 to 5. So let's start training. I'll keep ytrain here. All right. Now like I imported before, we're going to use the linear regression, ridge regression, and lasso regression. So I'm going to create a dictionary called models, which is going to map the name of the model, linear regression, to the actual instance of the model. So then we have ridge regression, which is also the same as L2 regression. So it's just linear regression with L2 regularization added, and this is ridge. And then we have our lasso regression, which is L1 regression. And that's going to be lasso. Now I'm going to just indent this so that they line up. Okay, and we'll call, we're going to fit each of them with a loop. So for name and model in models.items, the .items will return the key value pairs as tuples so that we can iterate through them 2 at a time like this. And then call model.fit on xtrain ytrain. And then we'll print out a little confirmation message that says the name of the model and verify that it was trained. Alright, and they're all trained, and now let's get the results. So again, I'm going to iterate through for name model in models.items. We will take the model and fit it, we're going to take the score of the model this time, model.score, xtest, ytest, so we're evaluating the model on the test set. And .score will return an r² value if in the case of regression. So we'll print out the name of the model and r² score. And I'll display the r² score to 5 decimal places, and we'll format that with model.score. Alright, let's see. Alright, and there we go. So the r² score can take a value at most, it can have a maximum value of 1.0, which means it's a perfect fit. It's basically a measure of how dispersed the data is around your fit. And you can see the lowest, there's no lower limit of how bad your fit can be. We have this linear regression score of just a terribly negative r² score. So this is basically just completely failing to complete the task. Very, very poor. Our lasso score is much better. It's very close to 0, which is still not great, but it's certainly better than this. And then our L2 ridge regression is doing the best with an R-squared score of 0.41. So in this case, ridge regression is a significant improvement to both of the other models. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.